up the complicating factors of SN1. Primarily, we'll look at methyl shifts, stereochemistry, do some review, and then at the end of the slide deck are some open slides and questions. So one of them we'll look at is ring opening, to reduce ring strain, or carbocation shift. And then I have a textbook questions associated with the textbook. We'll do some problems for that, fill up the time. And then you have your exam 4, that's going to open today at noon, and then you have 24 hours to do that. You also have the lecture quiz for today that's due as well. So those both open at noon today and close at noon tomorrow. Any questions before we get started? So we had ended last time on a hydride shift. So normally these things are 1, 2, and that's relatively speaking. So wherever your carbocation is, that's position 1, and then position 2 is next door. So if it's H, it's hydride, where it's the electrons in that CH bond are moving over. Methyl groups can also shift, and then alkyl groups themselves can shift, and we'll see that in terms of a ring opening. So let's look at this question here, where we have a secondary iodide treated with ethanol. And again, when you look at those conditions and diagnose it, the secondary is sort of the red flag about whether it's going to go SN2 or SN1. And then you further diagnose the conditions. So notice it only says solvent ethanol. So that's a polar protic solvent. There's no strong nucleophile. So ultimately, we would say this is going to do an SN1 mechanism. And again, that matters in terms of the rate limiting step. Rearrangements can occur, and then ultimately for stereochemistry, there can be inversion. So that's why it's important to diagnose the conditions. So when we look at, I know this might be hard to see here because it's in purple, but that's an iodide right there. And so that's the secondary iodide. And then when you look at the product, we're forming an ether. And that comes from the alcohol solvent. But what's different now is, so see that carbon in blue, it starts with 2 methyl groups, and then in the product it ends up with 1. And then we're seeing that O-ethyl bonded to that carbon. So something has had to happen to one of those methyl groups, and then ultimately the O-ethyl, the ether part, is trapping at that blue carbon. The other sort of red flag about what we're starting with, since it's a secondary halide, the carbocation stability trend is tertiary greater than secondary, much, much greater than primary. So if you are starting with secondary, you have to look at the beta carbons to see if you can do a rearrangement. And so they only go the one way to form more stable carbocations. And I think we have enough room on this slide to get through it. So the rate determining step is going to be ionization of the CI bond. So there are the ions, the carbocation and the iodide. We start with a secondary iodide, and that generates a secondary carbocation. And so if we're using this nomenclature of that being the alpha carbon, there's two beta carbons associated with this. So I'll say beta and beta prime. So beta has two hydrogens. It also has this bond here, which I'll call that bond an alkyl group. And then beta prime has methyl, methyl, and an alkyl group. So in the flow of this, we're really looking for an H, a methyl, and then maybe if the situation arises, an alkyl group shift. So at beta, if we were to shift over a hydrogen as hydride, what would the resultant carbocation there be? It would still be secondary. So in general, that would be called a degenerate rearrangement. And energetically, it's sort of degenerate means equal. So it's really not preferred or allowed. So you wouldn't go from one secondary to another secondary. You really want to form something that's more stable. So at this carbon, we have these two methyl groups. So they're equivalent. If one of those shifts over, what would the resultant carbocation there be? You'd have 1, 2, 3 groups, so that would end up being tertiary. And so that's what happens. Now keep in mind, this arrow is going to look a little bit funky. It's taking the 2 electrons in that bond with it and migrating over to that carbon. So that's what we mean by a 1-2 shift. So when that happens, we're now going to a tertiary carbocation. Maybe one thing I can do to make your life easier. So I tend not to put these hydrogens in, but don't forget that they're there. And so when that migrates over, now it's tertiary, it's more stable. And then since the molecule is surrounded by solvent, now that solvent, which is a polar protic solvent, is both a nucleophile, so it's going to attack that carbocation. And probably what happens, iodide is probably not a good base to do the proton transfer. It's another molecule of ethanol that will form the neutral compound. So what I mean by that is it's probably forming that conjugate acid of ethanol. And that's how you would explain the methyl group moving over and then that carbon getting trapped by the solvent. So the take-home message is to classify your initially formed carbocation. Look at all the beta positions. And for lack of a better way of saying this, like game out the scenarios in which these shifts can occur. And then analyze the newly formed carbocation. Will it be more stable or less stable? And again, if a rearrangement is possible on the energy coordinate at that intermediate, that's where it can go one way or the other. And again, that's going to be the divergent path that can lead to two different products. Any questions? So this was the empty slide for that. So as I stated before, when the leaving group is ionized, the carbocation is sp2 hybridized. So the plus charge resides in those p lobes, or the lobes of the p orbital. And since the lobes are sort of on top and below the plane of the three substituents, when the nucleophile attacks, it can attack either face equally, and that will racemize any existing stereocenters. So in the example shown here, this is a tertiary bromide, and so it has the S stereochemical designation. And then it's being treated with a solvent mixture. So in this case, the nucleophile is water, but it's a mixture of water and acetone to help solubilize things. So again, there's no strong nucleophile, so it has to go SN1. And then when this bond ionizes, the carbon is now sp2. And maybe I'll draw it here. So we know that water is going to be the nucleophile, so it can attack this lobe or that lobe equally. And then when you look at the products, you know, we could say this was retention and that was inversion of the stereocenter, but you form them equally. So you get a one-to-one mixture. And if you were to put that in a polarimeter, the specific rotation would be 0. So again, that highlights one of the main differences between SN2 and SN1, because SN2 is, I want to say, a concerted process. The nucleophile is attacking the electrophile, and then the inversion is happening in the transition state. Now, for SN1, because you're ionizing, you're forming an intermediate that's longer lived. And the nucleophile, again, will attack from either face, leading to racemization. But still, you know, as we go through this stuff, you have to keep in mind everything we learned about spectroscopy. How are people figuring these things out? you know, that there was inversion, there was racemization. So the polarimetry still matters. Obviously, the carbon proton uniqueness matters. And then in general for substitution, when you're going from one functional group to the next, keep in mind important IR stretches of those functional groups. So a couple of review questions, and then we'll do a summary slide and then some more questions just to check in about nomenclature and all that. So for an SN1 reaction, again, the 1 is for the kinetics, and that's unimolecular, so A and D are out. And again, that relates to the ionization of the carbon leaving group bond in the electrophile. Solvent, now we want polar protic, so we can eliminate C. And then the nucleophile has to be weak. And apologies for my chicken scratch here, neutral. The nucleophile has to be essentially neutral. So you don't want one of these situations where it's ionic with a cation and an anion. And again, all of that relates to how the intermediates in transition states are stabilized by the solvent. A question? So I guess the key for that is that the solvent in the nucleophile are essentially the same thing. They're usually alcohols or carboxylic acids. So, and for the most part, you know, they're the lower molecular weight alcohols. Because really at that point, I would say any alcohol that can be miscible in water is probably a good one. When you get up to like hexanol, that's probably no longer a good one because it's not soluble in water, which means it's not going to be a good ionizing solvent. So acids, CO2H, formic acid, acetic acid. We learned about bumping up the the pKa, trifluoroacetic acid. And again, those things that can help tug on the C leaving group bond to ionize it. So halogens will ionize. You know, chlorine, bromine, and iodine are good leaving groups. Fluorine, not so much. With alcohols, you always have to treat them with acid so that you protonate the OH, in that when it ionizes, it's forming water and a carbocation. So in the 4 alcohols shown, which one will get protonated and then ionize the fastest under the SN1 mechanism? So which one can you eliminate first? Huh? What? Sorry, I'm still sick and my ears are like half clogged. I would say first you can eliminate A. So look at the carbon in which that OH is attached to. So that carbon is sp2. Again, we're dealing with the leaving group being bonded to an sp3 hybridized carbon. So if it's sp2 or sp, it's really not even going to react. So all of these are sp3. So now the next thing I would say is classify what type of alcohol it is. And for alcohols, you're looking at the carbon bonded to the OH. So B is secondary, C is secondary, and then D is tertiary. So when it says ionize the fastest, that OH2 is going to leave and form the most stable carbocation. So which one of those now do you think will win? So D. So D's the winner. So when B and C ionize, they form secondary carbocations. In a race between B and C, B would win because it's secondary and allylic. So D is the ultimate winner because it's tertiary and allylic as well. Yeah.
Do SN1 and E1 basically parallel each other in how they act, except one impacts the carbon and one impacts the
So you're getting to why I designed the course the way I do, because like this is a supplement to your like textbook. It's like a problem thing, but most textbooks shove substitution and elimination in one chapter. And I've found over the years it's too much for students to diagnose, because then if you have 4 things to look at rather than like 2. So this exam is only on substitution. So where it gets fuzzy is when it's elimination. And so that's E2 and E1. So maybe just let me make a note here to show you what you're looking for. So SN1, so E1. Where it gets dicey really is when you have these bases. So with SN1 and E1, things will always be neutral. But then SN2, E2, where it gets dicey is now you have this thing, sodium ethoxide. That can act as a nucleophile, but most generally these are bases. And so to answer your question, this is going to go after a hydrogen to abstract it rather than a substitution, which it would do in SN2. But it just adds to the layer of, after you classify things, typically when you're dealing with a secondary substrate, then you look at the conditions. To hedge my bets like any other organic chemistry professor, you'd probably get a mixture of things. You'd get a mixture of substitution, and then you would get some elimination products. And then, just as a preview, so E1 and E2, they form alkenes. And so that's the focus of Module 5, is the chemistry of alkenes. But yes, it gets harder to figure out what is going to be the major thing. So let me see what is up here that slide. We'll do the substitutions and then ultimately the same thing for eliminations, and then we'll have a giant one for all of them. So,
Thank you.
yeah. So this says which one will not undergo. Again, it was A because the SP2, maybe since we do have time, I promise I'm not stalling. Let me just explain why A is not good so that we understand what that benzene ring is telling us. So that would be if the phenol got protonated. And we say now that bond is going to break to ionize to form water. This carbocation is super high in energy because the plus charge is not in a p orbital. Because look at that carbon-carbon bond right there. That second line means the p orbital on that carbon is tied up in the double bond with that carbon. So the plus charge is residing in an sp2 hybrid orbital. And maybe a better way to visualize that. So that would be like the sp2 hybrid orbital. And that's much higher in energy than the plus charge being in a p orbital. So this is actually called a vinyl carbocation. So there'll be some more slides in a little bit about that nomenclature in these positions and why it's important to understand ultimately where the plus charge is residing. I have a So here is a sequential problem where we're going to start with 2-methylbutane. We're going to do radical bromination and then take the major product of that and treat with ethanol and heat to determine which of the following, A, B, C, or D, is the major product. So what do we know about what do we remember about bromination under radical conditions? So bromine was the most selective. So in terms of the uniqueness, we had primary, tertiary, secondary, primary. So bromine is the most selective, so it's going to go after the tertiary CH. So it's going to substitute there. So we end up with a tertiary bromide. And then looking at these conditions, it's tertiary. We're just given ethanol, so this is SN1. Because you're starting with tertiary, it's not going to rearrange. And so the substitution is going to happen at that carbon for the ethanol solvent. So the answer for this one would be B as in boy. So here's a series of carbocations, and it's asking you which one will undergo a 1,2 hydride shift. First thing to do is just classify the carbocation. So this one's primary, secondary allylic. And then what do you think D is? So it's sp2, so that's vinyl. So that one, again, we can take out of the running because it's not going to do anything. It's super unstable. So let me draw this out a little bit. Do you think choice B would undergo a rearrangement? So if we look at B, there's the alpha carbon, there's beta, and beta, they're the same. The only thing that could happen is if a hydrogen moved over, you'd form a secondary. So it's really not gaining anything through that. C is secondary allylic. So it's sort of already resonance stabilized, meaning that if a hydrogen from this beta carbon were to move over, it would lose the allylic stabilization. So the best answer is going to be A. So here's our alpha carbon. There's only one beta carbon, there's the H. When that migrates over, we're now ending up with a tertiary allylic carbocation. So again, it needs to become more stable for that pathway to be preferred. Yeah.
Would that still form a resonance structure? If yes, then would the resonance structure be a secondary allylic? Or
Yeah, so it would form that resonance form. And again, what you have to realize when we're drawing these like separate, really it's just one thing. And so the way to think about like these plus charges, I'm just making up some numbers in my head, but maybe 75% of the plus charge is at the tertiary position and 25% is at the secondary. So it's not shared equally there because the tertiary of those resonance ones is more stable.
When it comes to classifying beta and beta carb, is it just a way to differentiate the two, or is there something specific about beta and beta?
So like I called these beta because the molecule's symmetric right here. So beta and beta are the same. Like if they're different, then I just use the prime. Yeah. The what now?
How does the options exist if any feature?
So for option C, the allylic resonance.
Yeah, how it is that?
So you have 1, 2, 3. That plus charge is going to move over to carbon 3 there. So in that case, C, you could probably think of the plus charge being equally distributed at carbons 1 and 3, as compared to choice A, where it's going to be different based on the classification. Yep.
Identify nucleophile strength.
So our table, as we know it so far, the promoting factors and the characteristics for substitution, SN2 and SN1. For the electrophile, allylic and benzylic are going to be special cases for each, but SN2 is the rate methyl is greater than primary, greater than secondary, and tertiaries do not react. And then for SN1, it's the opposite, where tertiary is greater than secondary and primaries do not react. The leaving groupability is pretty much the same for both. Nucleophile strength for SN2, you want it strong in terms of the ionic form. SN1, you want it weak. SN2, you want polar aprotic solvents. And again, the aprotic helps stabilize the metal of the ionic nucleophile. For SN1, you want the protic solvent that will help ionize the leaving group bond. The solvents are shown here, so DMSO, DMF, acetonitrile, hexamethylphosphor-triamide, acetone. For SN1, either acids or alcohols are good ones. The kinetics, that's what the number stands for, the 2 or the 1. There's the rate equation. For stereochemistry, SN2 gives you complete inversion. And then SN1 is racemization. So for rearrangements, that's only possible for the carbocations. Any questions? So again, with the elimination stuff, that's just going to add more complicating factors, but then you really have to look at the nucleophile if it's behaving as a base or a nucleophile. Yes?
Can you show how the previous slide, the C exists in
So really you're looking at ionic versus neutral. So in terms of ionic, say sodium cyanide versus hydrogen cyanide. And to show that further in the space here, so Na plus Cn minus is that writing? I don't know how much shows on there versus here. So keep in mind that the job of the nucleophile is to supply those electrons. When it's ionic, like they're right there. Like it's ready, once the metal moves away, it's ready to bond. In the neutral, now it's shared. Carbon might own a little bit more of that polar covalent bond, but it's shared, and there's really no opportunity for this to be as nucleophilic as that can be when those electrons are just ready to go. So typically you're looking at the ionic or neutral form, and then in terms of strength when comparing different nucleophiles, that trend runs opposite electronegativity. So a carbon nucleophile will be a better one than nitrogen. And then going down the group, sulfur would be better than oxygen. If you're comparing like the same sort of nucleophile, but a heteroatom is changing. So a couple of questions, and then we'll wrap up with an example or two, drawing out some mechanisms. So this is the other problem with all the OHs now in one molecule, basically. So it's the same thing, just stated a different way. Which of the following oxygens is most likely to undergo protonation ionization for SN1? So right away, we can eliminate the one bonded to the aromatic ring. That leaves us the other three. The next layer that we do is classifying them. So this is secondary, primary. So we're left with two secondaries, but one is special. Which one do you think that is? So this one right here is benzylic. And again, that's the sp3 hybridized carbon bonded to a benzene ring. So that gets protonated, the bond ionizes, and then the carbocation is stabilized by the ring. So you can move that plus charge into the ring by migrating the pi bonds. And then you can do that 1, 2, 3, I think 3 or 4 more times. So the more times you can delocalize that, the more stable it is. Yeah.
If we protonate the alcohol on the regular to secondary carbon, the plus charge goes there, right? But what if that happens and then there's a hydride shift, or is that not possible?
Yeah, so that's it is possible. It's called a Pinnacle rearrangement. So when you have this situation here, where you have two alcohols right next to one another, that's called a Pinnacle. And so yeah, you could protonate maybe a less unfavorable one and then get a shift. So that's its own name reaction. I would say it exists, but it's sort of beyond the scope of this material. So what reagent is likely to initiate an SN1 reaction with an alcohol? So this is where, again, you have to have an intuition about what these reagents are doing. So this is an ionic compound. This is an acid. This is an electrophile. This is a base. So if an alcohol is getting protonated, it needs to act as a base to react with an acid. So sulfuric acid would be the best reagent to kick off an SN1 reaction. What solvent would be best used for SN1? So if you just sort of look at the structures and add those key words to them, we need a polar protic solvent, so D would be the best. Hexane is nonpolar, so that's really not used in substitution reactions at all, SN2 or SN1. Diethyl ether is moderately polar. Propanone is more polar, so this would be appropriate. So SN1, SN2. In diethyl ether is really not used for substitutions either way. It's not polar enough. So I think we have a couple of these before the mechanism. So which of the following is the aromatic hydrogen? To switch the lettering around so everything doesn't end up being A. So this is the aromatic hydrogen. And again, the sort of intent of that is to identify it's bonded to an sp2 hybridized carbon. What about vanillic? So the difference between aromatic and vinylic, again, vinylic it's bonded to a double bond. And again, that's sp2 hybridized. So allylic is the sp3 hybridized carbon bonded to an alkene. And then lastly, benzylic. That's the one bonded to the benzene ring. So again, so we're not losing track of, the trees for the forest or the forest for the trees or however it goes. The point of understanding all this is you have to have some sort of rational path to predict the major product. When you look at all of these unique hydrogen sets, you don't want to start pulling your hair out saying, well, it can form like 5 different things. But the logic is really driving you into one of those sets due to their unique reactivity. So you always want to stay on the path, as it were. So let's see if we can start putting some things together, knowing what we know. So we have 3-bromo, 2-butanol. And we're going to treat that with sodium hydride using the solvent diethyl ether. and it's asking us what functional group would be formed. Do you remember what reactivity class is sodium hydride? Huh? So sodium hydride, it's a little weird, right? Because it's like, yeah, Na plus H minus. But in diagnosing the functional groups there, we have an OH bond. And so we have an alcohol with a pK of about 16. So that the hydride is really not going to be nucleophilic in this sense. It's going to act as a base. So it's going to deprotonate the OH bond. We lose the hydrogen gas, and then it forms this. And so based on the choices you see as the responses, what do you think's the functional group name? And then what do you think happens? What? So I mean, if you think about what do you need for an acid? Do you have all the elements there to make a carboxylic acid? So we can eliminate that. The bonding pattern for an ether is carbon, oxygen, carbon. There's no nitrogens in there, so we can eliminate amine. And then there's really no carbonyl at all. I mean, we already eliminated A. That has a carbonyl. So it's got to be an ether. So what do you think happens based on what you see there? So normally you're used to seeing the nucleophile and electrophile in two different molecules, right? So in this, they're the same. This is called intramolecular. So the O minus is the nucleophile. It's attracted to that carbon bearing the leaving group. So it's going to form this ether, which is called an epoxide. And so why does this happen even though it's forming something with ring strain? Those things are right next door to each other. So not much has to happen for that nucleophile to see that electrophilic carbon and just slam shut. So if you go on to 256, we'll talk about epoxides next semester for maybe a couple lectures. They're unique functional groups. You can do a lot with them. Let's skip this one. I want to do this just to show you, as promised. We talked about hydride shift, methyl shift, and what about an alkyl group shift? And again, these typically happen when a ring can expand. And so usually you're going one size up. So we're starting with a 3-membered ring, and we're forming a 4-membered ring. So we have the starting material, we have the product. We just really need to draw a possible mechanism of how this happens. And when we classify that alcohol, it's primary. When we look at the conditions, there's really no strong nucleophile. So if we say it's SN1, something's sort of not jiving with primaries never doing SN1. So what can happen, we know that we're treating with acid, so the alcohol is going to get protonated. So I can show it stepwise, but really ultimately you want to think of this stuff sort of happening all at once, where the ring expands to shove out that OH group. But if we draw it stepwise and this ionizes, that's a primary carbocation, which we said was bad. But if we look at the beta carbon now, you have a hydrogen there, but you also have these other groups, this bond and that bond. It's preferred that the bond actually migrate over. And so if the electrons in that bond move over, that means the plus charge moves over to the beta carbon. So let me draw it without moving too much stuff around. And so that's equivalent to a square, cyclobutane. So now it's a secondary carbocation. And then that can get trapped by the solvent. And we'll just use water for the acid-base reaction. So the reason this happens, or again, if I show in blue, you know, if you have just this bond opening up all at once, so like in a concerted fashion, it's not really going to form the primary, it'll just ionize and go right to the ring expanded secondary. So the reason this happens, relieve ring strain. So we know that going from 3 to 4 to 5, 6 is the most stable ring, if we recall what we learned in Module 3. You'll get these alkyl group shifts to relieve ring strain. So I had planned to do some stuff from here, but again, we're sort of out of time. I think the exam is doable. You'll have to refer back to the bond energy charts for a couple of those. So in your notes from the radical reaction, you need those bond homolysis energies to do some calculations. But everything else appears to be straightforward to me. I guess we'll find out. Again, it's due tomorrow at noon.